I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism Podcast, an exploration of the past, present, and future of material science and engineering. My name is Taylor Sparks, and I'm joined today by Andy Cooper, and we're going to talk about autonomous labs in materials and chemistry. So, Andy, nice to meet you. Thanks for being here.
Thanks for having me.
And on your birthday, no less. Appreciate you making time.
Thank you.
Okay, well, we are delighted to chat with you about this. Autonomous labs are this really interesting and emerging technology. So before we get into that, maybe you can tell us a bit about yourselves. You are the director of the Leverhulme Center for Materials Design, Functional Materials Design here at the University of Liverpool, the director of the Materials Innovation Factory, the director of the Center for Materials Discovery. I don't know if you ever sleep, where you find time to do all this, but tell us a bit about yourself.
I sleep now and then. Yes, so I'm a chemist by training. Actually, initially started as a spectroscopist, then got into materials chemistry. And we've been using automation for more than 20 years in my group, but I guess it's only in the last 6 or 7 years that we've got into what you might call this idea of autonomous robots, that is closed loop optimization and more hardcore robotics.
So when I talk to people about this, oftentimes sometimes they think that this is not evolved at all, that this is as simple as, basically like the auto sampler on your X-ray, spectrometer. And some people think it's all the way out to like Jarvis from Iron Man. So in your opinion, what is the current state of things? From 0 to 10, where are we?
Yeah, well, I guess I would say it's neither of those. For sure, I think it's been more of an evolution than a kind of single breakthrough moment. So I guess you can chart it back to what's the single most biggest development? Probably the peptide synthesizer, right? Which is quite...
Tell us about it.
Well, peptide synthesis allowed chemists and then later biochemists to make peptides on demand using a machine in an automated way, and it basically caused an explosion in biotechnology. But this was related to a very specific type of chemistry, peptide couplings. So I guess that was the foundational example. What has turned out to be the case is broadening that concept to all of chemistry is a much broader thing, right? Because chemistry is so diverse, from solid state chemistry to organic synthesis and heterogeneous catalysis. Yeah. So I think it's not as if there's been a sudden breakthrough in the last 5 years. It's been evolution. We started doing this 20 years ago with instruments made by a company called ChemSpeed, but they were not autonomous; they were automated. So it's not a Jarvis moment, but it's more than evolution, and I think the rate of progress has really accelerated a lot in this field in the last 5 to 10 years.
Can you point to the killer app where we couldn't have done it if it wasn't for autonomous? The thing that comes to mind is AlphaFold, right? The thing that really changed a lot of people's minds about artificial intelligence in science, I think, was AlphaFold, because here you had this 50-year-old problem. How do you simulate how proteins come together? And I remember when I was a kid, we had like screensavers and stuff, right? You could have your screensaver be folding proteins and you felt like you were pitching in to solve this grand challenge, and it was just not one that we had tackled and solved. And then all of a sudden, along comes AI, and it could, with machine learning, essentially predict what the conformations should be and do it with such good accuracy that they've sort of deemed this problem more or less solved. Do we have something like that we can point to in materials or chemistry? There's a few examples in materials I'm aware of, but I'm curious what you think.
I would say no, we don't, but then you're comparing two very different cases, right? So AlphaFold is an amazing development, but it's a very specific domain. It's how proteins fold, and it's computational. If you look at the concept, first you have to define what autonomous chemistry is, I guess. And if you define it, and I would define it as a closed loop approach, and if you consider that primarily initially as experimental, well, that's a much broader church than protein folding. Yeah. So there is no killer app. I think what we've got is an evolution of different hardware and different software and different camps, right? We use mobile robots, they integrate instruments in a lab. We can talk about that. Other groups use synthesis machines that go into a fume cupboard and make molecules. These aren't the same things, and none of them cover the whole space. So I don't think you can really make that comparison. I think it is fair to say, though, I'm starting to believe that the AI is outpacing the hardware. So the potential for AI perhaps is developing more rapidly than the associated hardware to do the closed-loop experiments. So that's something we're focusing on, is how to make this hardware more robust, more reliable. It's a slightly workmanlike thing to do, but it's needed, right?
So that said, is there a problem where you think it's going to be particularly apt to solve it, where people will then be excited about it? Like what would be the thing that will convince people?
Yeah. Well, I guess I have my biases, and I suppose I'm interested in what I'm interested in, but I think it's particularly applicable to things which are highly multivariate and not susceptible to sort of atoms up, design. We're working on heterogeneous catalysis, we're working on water splitting, actually, catalysts that can split water into hydrogen and oxygen. So that's been a long-standing challenge. The current materials are very far from practical realization, so if you could find those through autonomous closed-loop experimentation, that would be a proof point. You could think of others, sort of cure for cancer, other things, high temperature, room temperature superconductors. But I think it's particularly applicable to things that don't yield to human design and, I won't say intuition, knowledge, because they're too multivariate.
Yep, I've long felt that. And humans do a great job of thinking in lower dimensions, but as soon as you start adding dimensions, we just don't see the patterns. And yet we can find those pretty efficiently with AI tools. So, all right. That said, one of the reasons I came to Liverpool on my sabbatical was precisely because of this push towards automation. I had a friend who was here. He told me about the Materials Innovation Factory. I read the Wired article. I saw the robots. I said, this is a really cool place. Where I work on generative materials informatics, where I'm trying to actually come up with suggested new compounds, the limiting step for me is definitely how you go about making these things. So I was excited to come here and see the robots. Do you want to tell us a little about what's going on here in terms of automated experiments?
Yeah, well, there are a few things going on. We have worked with automated chemistry platforms in Liverpool, really, as I said, for nearly 20 years now. So in the Materials Innovation Factory, we have a large physical robot embedded integrated system that will find formulations, for example, in collaboration with partners in industry. So complex formulations, mixing things together, with a longer term aim of coming up with things with lower carbon footprint, higher performance, and so on. These are big machines. Like one of these robots is the size of the lab that I had when I was first appointed in Liverpool, actually. But we've also, in parallel with that, got this more modular approach, which is mobile robots integrating what you might call a traditional chemistry lab. And we think that's great for materials chemistry because, materials chemistry use lots of different techniques, lots of different instruments. So the idea is to automate the chemist rather than automating the instruments and building large physical installations.
So when I was reading that article talking about one of these mobile robots, it was a Kubo or something like that. Kuka. Yeah, I mean, it was a really cool machine. It's about-ish the size of a person, so it can sort of, traverse the room and do its things. But I remember in the article it talked about how long it took to sort of get this thing up and running. It sounded to me like it was essentially a PhD student just to learn how to program this thing and make it work in this space. Can you talk about some of the challenges that went into that? Like, was this a pretty massive undertaking? How much came from the company support versus doing it yourself?
Yeah, well, there's an interesting story there. So it started out as a collaboration with robotics researchers in Liverpool, and our part really was the chemistry. But then the lead academic went to work in a large software company. So very quickly we're running this robot chemistry project and we don't have the roboticists. So in the end, it was mainly done by one PhD student called Benjamin Berger, and we kind of had to assimilate the knowledge and learn the robotics. So yeah, that was a baptism of fire. I could give you a million stories. Maybe the most dramatic is the robot weighs 400 kilos and it broke the lab floor. So we had to actually have the whole lab stripped out and put a new floor in, which cost nearly as much as the robot. That was, I guess, the biggest step.
Was it just like a tile floor? It's like a piano essentially rolling around all day long.
It was a former teaching lab, and it had a sort of sprung joist wooden floor. The thing weighs 400 kilos, and like you say, it's like a piano rolling around. It very quickly wore a kind of track in the floor, which then had to all come up. So yeah. I mean, fortunately, most buildings now are not science. Science buildings are not built with wooden floors.
Sure.
Concrete floor, it works just fine.
Wow. So if somebody tomorrow said, hey, I want to do this, sounds amazing, can they benefit from all the work that you've done in years past to sort of bypass these problems?
Oh,
Or
yeah.
are they going to have to go through those similar learning curves?
Yeah, I mean, a few things to say on that. I mean, robotics is genuinely difficult, right? So to make robust automation of processes with chemistry which are safe, that's a hard task. The precision required is fractions of a millimeter for positioning things. It's hard. That said, we probably reinvented the wheel a little bit in the early days because we were coming at it as, chemists. But we've developed some methods, and they are entirely building on known methods, I should say, but methods for positioning very accurately the arm and the robot base. And I guess when we started the project, which was in about 2016, that technology was on the cusp a little bit, but that's much more established now. So,
can you tell us about it?
Yeah. So we started off with a touch method, where we have a block and the robot touches the cube on three faces and gets its X, Y, Z coordinates from a kind of calibration cube. The interesting thing is it can work in pitch darkness, and we did that initially for some project.
How does it find the cube? Is there some sort of
Right.
RF signal or something it
It has a
follows?
secondary location system on the base, which is a laser scanning method. So it maps the lab to sort of centimeter precision using the laser scanner, which is a technique called LiDAR, kind of like radar.
Yeah.
So it finds the cube with radar, then it touches the cube, and then it can position itself to within sort of 0.2 of a millimeter. The interesting thing is that could be over like half a kilometer. Right? Turns out we've now come up with another method which is also used widely in robotics, which is positioning of using cameras and QR codes, which is essentially the same, but rather than touching a cube, a camera cites a code. The long story short, it's accurate to the kind of accuracy that you need for manipulating lab objects.
Okay, so it can find itself. What if something gets misplaced? Do you find that it's breaking things? Once it finds itself, it assumes that there's a clear path to set the sample on the dish or whatever it is. If something gets in the way, is it still breaking things?
Initially, yes, and we used a technique which is effectively dead reckoning. It assumes that everything is where it should be. Right?
Okay.
So then you have the phenomenon of picking up a phantom vial that actually isn't there if the student hasn't loaded it up right. We've since graduated to the point where we're building a secondary sensing system, so the robot can check that it is indeed picking up a sample vial.
Yeah, so it doesn't pour a dangerous chemical into nothing.
And that, yeah. So that's a whole big area in itself. Actually, not all of which we will address, but safety in labs. It's related to safety for robots in assistive care in homes, for example. As you know, although they don't weigh 400 kilos, they're still working in a space with a human and.
So cool. I first saw a talk on this at some conference somewhere where they talked about just the challenge in getting things to line up was enormously difficult. They were relying on sensors. They basically put little tiny sensors everywhere, and that was what they did first. And then they had moved, sounds like you did the same thing, towards computer vision. I'm not surprised. Image segmentation, all these tools have just massive leaps forward. It's getting better and better and easier to in real time have the computer see, much like we see, and make decisions based off of its surroundings.
So we also have some projects where we're using that not only for positioning. So myself and my colleague Gabriella Pizzuto are working on using cameras and image segmentation to actually estimate properties. One will be viscosity. So we've got a paper.
Just by looking at it.
Yeah, we've got a paper
cool.
that we just about to submit on manipulating liquids and looking at the flow.
Like the time response?
Essentially, but we're doing it by training using a convolutional neural network rather than a kind of hardwired,
so cool.
metric.
So
basically, you can estimate, whether something is water or honey, by looking at it. Turns out that the robot can do much more than that and can make much finer distinctions. It's another example, actually, where AI beats human perception.
Yeah, for sure. It was fascinating to me to talk to one of my peers that's here in Matt Rosinski's group, and they're starting to automate some things. And one of the things they've come up to is like, just some things are really tricky, and it's so easy to have a human do it. The example that they gave me was grinding things in a mortar and pestle. Every first-year grad student that does solid-state chemistry does this. You put the things in there, and you don't realize how finessey that is because you have to sort of grind it. You can't let the stuff go flying everywhere. You sort of scrape it back down in the middle. How do you teach a robot to do really finesse things like that?
Yeah, well, we have a project that's very much in that area, but it's commercial, so I can't really talk about the details. But in general, that is a hard problem. Another project I can talk about which I can talk about, is crystallization. So we're growing crystals of organic materials from a solvent, and then we want to get the X-ray diffraction for the crystals. And it's the same problem. You need to scrape the crystals out of the vial, which may be stuck to the walls of the vial, obviously without using any solvent. You need to grind them up at some level to reduce the particle size for X-ray diffraction and so on. And long story short, we've used a combination of single arm and dual arm robots to do that. So my student Amy Lunt, who's just finishing a PhD, developed a 2-arm robot that can effectively mimic what a human does using 2 arms.
So what do you think in the long term, will we eventually solve even these, niche problems, or will we always have humans sort of in the loop doing part of these tasks? And this kind of goes to my next question, which is, should scientists be afraid that robots are going to take their jobs, or will the future look more like a symbiotic relationship where they're doing some tasks but not others?
Yeah, I mean, I don't think it's necessarily sensible to try to automate everything. I mean, my view is, in principle, everything is automatable, but the technical complexity of doing it varies enormously, right? I mean, so to answer that, I think pragmatic solution is to have hybrid systems, and we're beginning to do that. But I think perhaps even more interesting than the subject of, sharing tasks between robots and humans is sharing the thinking. I.e. the decision making, which is something we call human in the loop, which is sort of interfacing algorithms with human knowledge. As for your question about should people be afraid of losing their job, I mean, I would say largely no, because if you look again at the peptide synthesizer, it didn't take jobs, it created an entire industry and area of biotechnology.
Yeah. So there's a great paper out there in the journal Matter, which we're fans of, by Benji Maruyama and a bunch of others. It was sort of a community perspective on autonomous experimentations. And I like one figure they have in there. They essentially encompass all the things you need to consider if you're going to do autonomous experimentation. There's the initialization step where you're deciding what are the objectives, what's the design space you're going to work in, what's the prior knowledge. There's the plan phase where maybe you're going to be predicting properties. You have to balance this explore versus exploit. You have to make decisions, right? Then comes the experiment where you're going to make, characterize, and simulate things. And finally, analysis, where you're going to try and extract knowledge from your experiments, interpret the data, make reasoning. And then finally, you're going to conclude, right? Where you're going to report on your objectives, report this knowledge, update repositories. In a perfect world, an autonomous experiment could try and do all of these things. I think that some of these are much easier for robots than others, though. So do you want to talk a little bit about where you see robots actually making decisions in this sort of frame?
Yeah, well, I've seen that paper actually, and it's very interesting. It sets it out in a nice way. So when we talk about robots making decisions, and of course really it's algorithms making decisions more than robots, and up until now what we've done is more about what composition to make next. So you do 16 experiments, and based on the data, what are the next 16 experiments? We've used Bayesian optimization. We're starting to look at some other types of optimization. And there's a whole host of interesting work out there. Alan Asprey-Guzik in Toronto did some of the early sort of foundational work related to chemistry. But now there's a whole host of people doing that and coming up with clever optimization algorithms. And that's definitely still an important area of research, because there are, I think there are going to be more developments now. Bayesian optimization is a broad subject in itself, and there are other approaches. But to go back to your Matter paper, what has surprised me, and if you'd asked me 10 years ago, I would have said, well, the automation, the physical manifestation, and the algorithm is the hard bit. I'm now beginning to think actually it's step one.
I agree.
And I'll apply this to myself too. We're not trained to think in the way of designing an experiment in an open-ended kind of closed-loop fashion. We're totally trained to think in sort of taking a material or a catalyst and making some modifications on it, usually relatively incremental modifications. So to step into the unknown and say, right, we're going to do a huge open-ended experimental search, let's load up 50 chemicals into the system and let it rip, is incredibly difficult, and it's much more difficult than I gave it credit for. And I think I'm beginning to think it's much harder than the automation. Of course, the automation is hard too, but once you have the tools to do these things, you've got the sobering realizations like, oh, what do I do with it now, right? And I did not expect that, because I thought we'd build the thing and do 1,000 experiments. Actually, it's much harder than that, and it's a training thing, and it's a culture thing, and it's sort of, you need to really start to think from first principles about the problem you're addressing. In some cases, in a high dimensional space, it's very difficult. I think we need software tools to help us with that, which currently don't exist.
I agree.
And it goes beyond design of experiments.
Yeah.
It's something about interfacing with the human knowledge base. I'm not talking here so much about natural language processing.
No, things like knowledge graphs, I think, are going to start to be really important.
Knowledge graphs is one example, yeah, but again, this is a training thing, right? And sort of PhD students who have au fait with that to a first approximation is nil, right?
So let's talk about that a little bit, because this is something I bump into all the time. Just last week we were talking in my department about, should we have a data science course, right? Should this be part of the curriculum for material science? In your view, how are we going to train this next generation of chemists, material scientists that will operate these tools, integrate with them, be hybrid with them? Where does that fit in the current curriculum?
That's a good question. I think some of it is beyond undergraduate level, right? I still think there's a lot of the current undergraduate curriculum that is fit for purpose, because if you don't know what a semiconductor is, then you don't need to worry about a knowledge graph for describing semiconductors, right? So I think we're probably talking master's, PhD level training almost, I guess, mainly. But I think having a pipeline of undergraduates who are more data literate, who know more about coding, and actually statistics, right? Statistics rears its ugly head, and it is ugly head in this area too.
Yeah.
And most chemists, and I hold my hand up, I'm not a statistician.
Yep.
So I wouldn't say I have all of the skills, and I still routinely feel like I'm reinventing stuff which mathematicians know and which computer scientists know, and then being told, you're doing it in PowerPoint, but there's actually software.
Yeah.
It happened to me the other day. I was trying to construct an ontology or sort of description for an experiment, and one of my colleagues pointed out, you're drawing this stuff by hand. There's been software available.
Of course there is.
20 years to do this, right? You're reinventing the wheel, really, in a big way.
There's this quote by, I want to say it's Bolton, I might be getting it wrong, but the idea, the gist of the quote was that each incremental bit of knowledge is harder to earn than the last, because you have to understand the previous before you can do the next. And this is, I think, a challenge, because as scientists, the way that we've gotten around that is by going to more and more niche areas of research. I'm not a chemist, I'm a biochemist. I'm not even I'm a solid state chemist. And so that's how we've gotten around it, is saying, well, I'm not going to worry about that other thing. I'm just going to drill down. But what I'm increasingly seeing is that the interesting things that are happening in the world are at these interfaces. Take chemistry and robotics, right? Where you can't just become more and more of an expert because there's too much to cover. So is the answer to work in teams? Is it more collaboration? Or what do you think is the answer with this challenge that we're facing?
Yeah, to me, it's 100% to work in teams. We managed to build this mobile robot. It was largely myself and my PhD student, Benjamin Berger, without a kind of robotics person on the team, but that is a really dumb way to do it, right? We did it, and I'm kind of proud of it, but it isn't the right way to do it, and we would have done it much faster with an embedded roboticist. We just didn't have the resources at that point. Since we have got people embedded who are roboticists, it's a whole discipline, and I think that goes for computer science, algorithms, optimization strategies, and so on. I am learning this stuff. When I say learning it, I'm sort of learning it A, slowly, and B, there's always too much to learn, right? So it has to be about teams, and I don't think it's a realistic aspiration or even a good idea to try to teach all undergraduates all of this stuff. I don't believe it's humanly possible.
You're going to be 10 years in by the time you've got your undergrad at that point.
Yeah, I think we need teams, and there's a lot of discussion about silos and sort of, well, as you say, segmentation of subjects into increasingly small domains. But at some level it happened for a reason, right? Is most people there just isn't enough time in a human life to learn all of this stuff, right? So you probably can't become an expert in all of these areas, and no one ever will. So I think we need to embrace teams and just go with that, because, my own experience is that works so much better, is to have teams of specialists who are interested in the cognate disciplines rather than one guy trying to know it all. I've tried that, and it drives you it drives you nearly insane, right?
Yeah. Okay, so you've got these autonomous labs, you've got the robots churning away day and night in the dark, right? All this data is being generated. What do you do with this data? You're not certainly not somebody's periodically going in with a USB stick and grabbing the data off the machine. How are you managing data?
Well, you might be surprised.
Is that still the case?
We don't know. We don't use USB sticks. I mean, but some of it right now for the academic work is fairly rudimentary, right?
Okay.
So a CSV file is uploaded to some folder, and then the algorithm operates on that, and there's a whole set of things about data integrity, lab information management, software type approaches. How do you collectively learn from data for a decade or 20 years ago? We're a university activity here, so there will be a need for that once these technologies become mature. Standardization of data, how to look at it retrospectively. I would say right now we're just not there. We're producing moderate amounts of data. I mean, important to say, 1,000 chemistry experiments, 1,000 reactions is still a huge number in chemistry automation, right?
Oh, yeah.
Whereas if you said I've done high throughput computational chemistry, 1,000 calculations, people are going to laugh, right? So the data size is currently not that big. So we're doing it in pretty traditional ways.
Okay.
Honestly, at the moment.
Well, you touched on something that's a major bugaboo for me, which is data format, right? What is the problem? So the problem to me, let me describe the problem as I see it. If you compare this to something like, crystal structures, we early on decided on the crystallographic information file, which was a strict format that everyone had to agree to if you wanted to publish in one of the IUCR journals. And that caused everyone to sort of get on board, and then that caused the proliferation of these big crystal structure databases, which has been a huge boon to science. And yet we can't get our act together and do the same thing for materials properties, for chemical properties. Mm-hmm. So that's the problem. What are some potential solutions out there to fix that? Because I've heard a bunch of people propose different formats, but nobody's coalescing around one. Are they not good enough? Are they not flexible enough to capture everything? Or what's the issue here?
Well, that's a very good question. Of course, the CIF file is a relatively, it's a nice one in terms of standardization. It's coordinates and atom identity.
Yeah, it's also very specific to a very specific problem.
It's very specific. If you look at the way that evolved, and again, I'm not expert on the history of this, but the requirement to deposit these structures, basically a culture coalesced around the Cambridge Crystallographic Data Center where there was a requirement, and there are some other databases now, but initially the CCDC. Well, you had to do it, right? So, and how did that happen? It happened, happened initially slowly, and now it's become the standard repository. But there aren't many of those. Of course, if you take a commercial angle here, instrument suppliers actually have some vested interest in some cases to developing non-standard formats, and they make money out of it, right? So I was at a conference where a company I won't name was
basically all of them,
which means all of them, was questioned about this, and interoperability isn't their business. They want things to be interoperable in their own ecosystem of instruments, not with everybody else's instruments, right? But I think that's beginning to be challenged now, and with this rise of some modular automation, I think companies are now. They've gone from being dismissive to having a watching brief on it, I would say, and saying, well, actually, this could become once this becomes a consumer demand, then they'll have to do it.
Yeah.
But I think, we're at a turning point now. But I notice a change in stance there from, this is our format, everything's closed source, to more discussion. I'm pretty sure in the next 10, 20 years that there'll be change there. But I think it will be a slow process because there's a lot of vested interest there.
Well, and it's hard too, right? We all know how to write papers, and it's sort of familiar, but you're going to train some academic that now, by the way, you have to submit in some sort of format all of the information. That's extra work, right? So nobody wants to take it. So on one hand, it's requiring people to do extra work, so you could say, okay, a journal's going to require it. But if a journal does that, it's sort of suicide for that journal. If a journal comes out with a really strict data management, format and says, if you're going to publish at Journal X or whatever it is, you have to abide by this, people are just going to go elsewhere.
This is a real discussion. So I'm actually the editor currently of Chemical Science, and we've had that discussion multiple times in editorial board meetings, and the direction of travel is open data, but you're a brave journal if you're the first to
That's right.
Require everything, because ultimately, journals want submitters as well.
Something that we are excited about, we're working with the journal Inorganic Chemistry. It's an ACS journal, and we are going to try a special issue where people can opt into it, and we'll just give it a shot, right? More importantly, we're actually building some tools which I am very excited about, using large language models to grab the data for you from the PDF. Let the authors produce the paper exactly how they've always done it, and then allow AI to try and scrape the data out. It won't be perfect, but it's pretty dang good. I've been blown away at how far we've come. Because 5 years ago, I heard people talking about LLMs to try, well, not LLMs, but NLP to grab data from literature. And I was like, I wasn't very impressed, but boy, I've changed my tune now.
So we've done some things a little bit in that direction, not using LLMs actually, but algorithms to script, pulling out certain data. But you have to be careful because you have to read the fine print of the sort of publishing rules and copyright rules actually. So that can become a grey area too in terms of the legalities. But I suspect that much will change actually, because again, it's difficult to take that stance. I think in the modern world that you're breaking our copyright.
Yeah.
Anyway, no one sues academics.
All right. Well, yet another podcast episode where I get derailed talking about machine learning and AI. But let's get back to autonomous experiments. Tell me about the cost of some of these labs. Are they, in my view, they've been prohibitive to a lot of labs. Is that changing? What's the state of it?
Well, everyone asks that question, but the strongest example I've got is the first thing we published on mobile robots. There's this workflow with about 8 instruments in it, but the high-performance liquid chromatograph that sits there like a beige box on the bench actually costs more than the mobile robot. So, I guess you've got to look at the context, right? So the robots we used in that first paper cost about £150,000. Sounds like a lot of money, but there are lots of instruments.
There's
that cost £150,000.
diffractometers twice that.
So we're now integrating diffractometers, which cost maybe 3 times so much. So I guess the point is, if the stuff works and actually increases your throughput, then it's not really expensive. In fact, because it's just saying. But of course, as a unit thing, it is quite expensive. It's expensive if you have to buy it and then build the entire software from scratch, right? Because you've got to think about the resources needed to develop all. We wrote all of the software from nothing, right? If there were a commercial a supplier, and I declare conflict of interest because we have a spin out in this area, but if there were a nice package that you could buy with the robot and the software, then I don't think it's so expensive.
Okay. Did I see on Twitter that you won a big new grant in this area? You want to tell us about it?
Is this the Royal Society research?
Well, I don't know what it was.
Yeah,
it looked exciting, though.
Yeah, it's not so much a big grant as it's a sort of Royal Society research professor position, which gives me the ability to focus on the research for the next 5 to 10 years. So it's kind of a research award more than a big grant. So what it will allow me to do is keep battling, breaking the floors and other things.
So cool.
Yeah.
All right, well, near to the end, can you tell me about, in your view, what are some of the big unsolved challenges where we need bright minds to tackle issues here?
Well, I think I referred to one of them, which is this, how to think about chemistry. And I genuinely think, if I had to choose one, that is the one, is how are we going to interface with these platforms? Because a lot of the other challenges, they will happen, like standardization of data, APIs, etc. These are all, there's no impediment there really. It's just a question of the market pull, I guess. But, how do we change our thinking? And ultimately teams, because I think these things are not going to get solved by chemists alone. It's going to take initiatives with teams, people from different disciplines. I think that's the fundamental one, and I can see that. I don't suppose we're alone in this experience of building a robot and then thinking, wow, now what do we do?
Yeah.
Ultimately, it does still come down to having good ideas about chemistry, and that's not going to go away very quickly, I think.
Okay. Well, it was a pleasure. Thanks for joining us today.
Thank you.
Yeah, talk to you later.
The Materialism Podcast is sponsored by Materials Today. You can visit materialstoday.com to stay up to date on the latest happenings in the material science field and read some of the fantastic articles that they've published. You can also head over to elsevier.com to find out more about their journals, books, conferences, and related programs.
We would love it if you would leave us a review. 5 stars on iTunes, Spotify, Google Play, wherever you're listening to your podcast. that will help other people find the show, and that would be pretty rad, we think. Special shout out to the people who make the music for the show. That's Alphabot and Kolobyte. I know we've said this like 65 times now, but if you haven't checked them out, you should do it. They make cool stuff. We dig it. Anyways, that's it for today. We hope to see you in the next episode. See you, everybody.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.